In this video, we're going to be going over another example related to design concepts. I'll let you pause the video so you can read over the question and attempt the question on your own if you want. In the question, we're given the allowable bending stress and the allowable shear stress for this box beam, and we're told to find the maximum distributed load, W, that the beam can support. We're also told to find the maximum safe nailed spacing for each 1/3 of the length of the beam, where each nail can resist a shear force of 200 newtons. Since the section properties and allowable stresses are known, we can first calculate the maximum distributed load based on the bending and shear stresses. We'll start with the first step, where we want to perform an analysis of the beam. This includes finding reaction forces at the supports. Note that this is a roller support and this side is a pin support, and we're left with these reaction forces. Then we can draw a shear force diagram as well as a bending moment diagram. From these two diagrams, we can determine the maximum shear force and maximum bending moment. Now we can move on to step 2. In step 2, we want to now design for bending using this equation, where the required section modulus is equal to the maximum bending moment divided by the allowable bending stress. We know that Mmax is simply this, which we found from step 1. So we can isolate for Mmax, then plug this value into this equation, and then isolate for W, which is the maximum distributed load that we're told to find in the question. Also note that this is given to us in the question, and this section modulus can be solved with the section properties were also given in the question, where S equals to I over C. Since this is a composite shape, we'll have to calculate for I, the moment of inertia, using this equation. I equals I outer minus I middle, where I outer represents the moment of inertia for this larger rectangle, and I middle represents the moment of inertia for the smaller rectangle. Simplifying, we get that the moment of inertia of the whole shape is equal to 187.7 times 10 to the 6 millimeters to the power of 4. To calculate for C, it is simply the maximum distance from the neutral axis, so for this shape it is just 250 millimeters divided by 2, which is equal to 125 millimeters. Now that we found I and C, we can plug the values in here and calculate for S, the section modulus, which is this. Going back to this equation, we can now solve for the maximum distributed load, which is equal to 3.34 newtons per millimeter, which is also 3.34 kilonewtons per meter. In step 2, we found the maximum distributed load based on the allowable bending stress. So now we're moving on to step 3, where we want to calculate for the maximum distributed load using the allowable shear stress. Then we can compare the two maximum distributed loads and see which load is the smallest, and the smallest load will tell us whether or not it is governed by shear or bending. Since our box beam is not a rectangular section and it's also not a W section, we have to use this equation, where in our case the maximum shear stress is also the allowable shear stress. From step 1, we found that this is the maximum shear force, so we isolate for Vmax here, plug the maximum shear force into this equation, and then isolate for W. All these values are known to us, so we can go ahead and calculate for Q. Since this is a composite shape, let's break up the shape into 3 components. Then to find Q, it is simply the summation of y prime bar times a prime at each component that we labeled, which can also be rewritten as Q1 plus Q2 plus Q3. So we'll first calculate for y prime bar 1 and a prime 1. We'll do the same for components 2 and 3. Note that components 2 and 3 have the same y prime bar and a prime. Now we can calculate for Q by plugging in our values, which will get the first moment of area is equal to this. Then we can find T, the thickness of the web. Since we have 2 webs with the same thickness, we'll multiply 30 millimeters by 2, and we'll end up with T equals to 60 millimeters. Now we can plug everything back into the maximum distributed load equation. Remember to make sure your units are consistent. We converted the units for shear stress to megapascals, which is also newtons per millimeter squared. And we'll have a maximum distributed load of 3.02 kilonewtons per meter. When we compare this value to the maximum distributed load we found using bending stress, we can see that by using shear stress, we get a smaller distributed load. This means that shear stress will govern and we'll have to use a maximum distributed load of around 3 kilonewtons per meter to satisfy both the shear and bending stresses. Now we can move on to step 4, where we can now calculate for the nail spacing. Some important things to note is that shear varies along the length of the beam, and we're told to design the nail spacing for each 1/3 of the beam. So let's split the beam up into thirds, so each section will have a length of 2 meters. So using the shear force diagram, when x is equal to 0, our shear force is WL over 2. When x is equal to 2 meters, our maximum shear force is equal to 1/3 of the shear force at 0 meters. The shear force when x is equal to 4 meters will be equal to the shear force at x equals to 2 meters, but it will be negative. And the shear force when x is equal to 6 meters is negative WL over 2. These shear forces can also be found by creating cuts along the beam. So for fasteners, we'll be using this equation. We just calculated for the shear force, V, at each section of the beam, and we already know the moment of inertia, which we calculated earlier from step 2. So we'll calculate for capital Q, the first moment of area, which is the section right here. And we'll end up with this. Now we want to find the shear flow at each third of the beam. Note that the maximum shear force between 0 to 2 meters and 4 to 6 meters are the same. Since we already calculated for the maximum distributed load, we can plug it in here to solve for the maximum shear force at these two segments of the beam, and we'll get Vmax is equal to 9 kilonewtons. Then plugging into the shear flow equation, we get that the shear flow is equal to 23.73 newtons per millimeter. Now to find the required safe nail spacing, we have to use this equation, where S required is the required nail spacing, F nail is the shear force that the nail can resist, which we're told in the question that it can resist a shear force of 200 newtons, and Q required is the required shear flow. Remember, in the question there are 2 rows of nails, so to account for that, we need to divide the shear flow we found earlier by 2 to give us the required shear flow for 1 row of nails. Then we can find the required nail spacing by subbing these values in, and we get that it equals to 16.8 millimeters. Since 16.8 millimeters isn't easily divisible by 6,000 millimeters, which is the length of the beam, then we will use S equals to 15 millimeters instead, because that's easily divisible by 6,000 millimeters. That also means between 4 and 6 meters, we will also use a nail spacing of 15 millimeters. We can now apply the same steps to the middle portion of the beam, where X is between 2 and 4 meters. We can see that the maximum shear force is WL over 6. So by plugging in our values, we get Vmax is equal to 3 kilonewtons. Then plugging that into our shear flow equation, we get that the shear flow equals to 7.91 newtons per millimeter. Remember, this value accounts for the shear flow in 2 rows of nails, so we have to divide it by 2 to give us the shear flow for 1 row of nails. Then plugging into the required nail spacing equation, we get that the required spacing is 50.6 millimeters. So we'll use 50 millimeters since it is easily divisible by 6,000. So to summarize, the beam can safely support a maximum distributed load of 3 kilonewtons per meter, and at each third of the beam, we should use a nail spacing of 50 millimeters and 50 millimeters. In conclusion, we were able to apply the general design process of beams into this example. That concludes this video, and that also concludes the course content.